years, and she was asking if you could think about how in your project work for this class you could advance the unit that we're going to show as part of what we're doing. So, as you go through this, you'll see lots of functions and sequence, and I know you're going to just jump on that and say, oh, model builder, wow, I could do this with model builder, yeah. And so those who are doing plug mapping projects might want to think about that, because that'll simplify what we have to do in the repeat process that we're doing for this class. So with that, Dr. Taberton.
I'll be happy to go. So if the guys in Utah can just wave if you're hearing me. Are you guys okay? So this is like kind of one of those events where your virtual life meets your real life. You met somebody over the computer and suddenly you see them in person. It's always an unusual thing. And I guess in terms of programming this in Model Builder, the class on Tuesday, I'm scheduled to talk about programming in ArcGIS. So we'll cover some of those ideas next time. But for today, we're going to focus on calculating hand and developing a rating curve and mapping inundation and the houses that might get flooded in Onion Creek. And it's not really a hypothetical exercise because it did happen tragically a few years ago. And so it's very real. We're starting off with some data that's been prepared a little bit for you. I spoke last time about the flow direction conditioning idea, and that's a little bit involved and not possible. Well, there's a tau-dem function that I actually had to write to do that. So rather than have you sort of go through that, which would have made it quite long, I've prepared the data. The DEM is already sort of set up like that. So if you take the DEM that I give you here and the DEM that you would get from the National Innovation data set, you would see that sort of a difference. So I'm just going to start, and first thing I'm going to do is attach to my project the database that hopefully is along with it. So there is this Onion Hand geodatabase is the database we're using, and inside that I took all the data and projected it into the UTM 14 Zone 14 projection, and we'll be using that. And we've got things like the NHD catchments, the NHD flow lines, and the address points, which are all the houses and other businesses and things that we'll be mapping. There's also in the data that's provided, I guess if we go into folders here, we look inside that folder, there was this onion3.tif file. I probably could have named it a little bit better. It was the third one in the sequence of going through the terrain processing. Are you guys, maybe yeah, it's pretty noisy out there. It's noisy in Utah. Is it always noisy in Utah? No. Maybe it's, okay. So let me add that DEM to the map. Don't know why it's taking its time to add. Did I actually drag it on? There we go. So let me symbolize these catchments with outlines by themselves rather than the filled in. So you can see there's the catchments, and make the NHD streams a deeper blue. So that's the data that we're starting with. We're going to be delineating streams from the digital elevation model, and we want to have the streams we delineate start exactly from the endpoints of these NHD streams. So that requires identifying the edges of what's effectively a network. And the function that's used in that, and you'd never guess, the keyword is dangle. So they refer to as dangling points. And oftentimes in ArcGIS, the hardest thing is to know the name of the function you're working with. Once you know the name, you can find it in amongst all the tools, and you're golden. So I'm going to go into the tools and search for dangle. And then we'll find the function is actually feature vertices to points. So the endpoints are referred to as vertices, and I'm going to convert them to points, and I'm going to select the inputs. I'm going to work on the NHD flow lines. I'm going to specify that the output is going into my feature data set, and I was just calling it vertices. And rather than all the vertices, which would get the internal junctions as well, I'm just going to get the dangling vertices. And now if I run this function, we should get a new result, all of these white dots. And if you zoom in on them, well, before you see there's one at the outlet, and there's one at the beginning of each stream. So say zoom in there, you'll see there's a dot at the beginning of the stream, a dot at the beginning of the stream, and so on. So we're going to have our streams that we map from the digital elevation model start there, and to do that we need to convert this into a raster to be able to use that as a function, to use that as input to the weighted flow accumulation. So to convert what here are features, points, into a raster, we use the feature to raster function. And let's see, somewhere we should find that. Feature to raster. The input features are going to be my vertices. Rather than using the field COM_ID, this is something that I figured out a little bit by trial and error. There is a field in there called start flag, and that evaluates to 1 if it's the beginning of a reach, 0 if it's the end of a reach, and that actually served as a useful filter for picking just the sources of the streams and leaving out the outlet point. So I'm going to use start flag as the feature. The output raster, I'm going to give it a name, and I'm going to put the name start TIFF. So I was using, I decided to do this exercise in terms of GeoTIFF files, partly for a little bit of historic reasons. The initial exercise last year was done in terms of GeoTIFF files with TauDem, and I thought it's previously, most of the time we've been working with rasters, we've been working with them inside the geodatabase. This is another way to work with them outside of the geodatabase, just files on the computer system that are actually more readable and transferable. You can read them in other GIS systems, not only ArcGIS. So I'm going to name it that. I'm going to actually put it at the top level folder next to this file that we started with. Before I rush to hit run, we all have it rushing to hit run here, we have to worry about the cell size. And I actually want the raster that I produce to have exactly the same dimensions as my digital elevation model. And I can control that. You see, it was picking a default size of 91.3 meters. I can control that by going to environments and setting the coordinate system to be the same as my digital elevation model, snapping it to that digital elevation model. That means the grid cells will line up, the cell size to be the same as that digital elevation model. And I'm just going to leave all of the other things alone. But if I switch back to the parameters of this tool, you'll see that now the cell size is switched to 10 meters. So now if I run that, it's completed. And if I say zoom right in on the end of one of these streams and I turn off the vertices, you'll see there's a little purple dot there. So that's what that function has basically created a raster with a single cell that has a value of 1 at the beginning of each stream, and it's got a value of 0 everywhere else. That was all up to page 3 and 4, and I haven't got this in my head yet to do it without looking at the notes. It's worth looking at the attribute table for this, and we can see that there's 42 cells with a value of 1, and there aren't any other. Well, there was one with a value of 0. That would have been the one at the outlet. You might say, what's happened to the rest of the cells in this raster? And they're actually all no data. So we're going to want to classify them to be 0, so that when we use a weighted flow accumulation, we don't have it trying to do calculations with no data values. So I'm going to go into the reclassify function, which I think might have used before, but it's a fairly common and useful function. I'm specifying this start as in the field I'm going to be changing as value, and it gives me some suggestions here. So what it's showing on the left is the values we currently have in this raster, 0 and 1 and no data. For some reason it wants to put 1 and 2 and no data. I actually want the zeros to remain 0. I want the ones to remain 1, and I want the no data to be changed to 0, and I want the outlet or the output to be stored, and I called it start RC .tif, and that we'll put it next to all of the other ones, and I run that. It's important when you do this to get the 0, 1, 0 on the right.
Can you please explain again why does it has 1 value as 42 times and 0 value as 1 time?
Because there were 42 of these vertices that inherited the value 1 from the start flag. There was one vertex, the one at the outlet, that inherited a value of the start flag 0, because it's actually the end of a stream reach. And it's only the ones at the beginning of the stream reaches that I'm really concerned about here.
How did this cat vertex got the value of 0?
So we could go into that. Let's, if I look at the attribute table, well, this was actually in the data that's provided. So this data was extracted from the National Hydrography data set, and that was generated. Each segment in the National Hydrography data set has a direction associated with it, and so there's a start and an end. And when you do the conversion from the features to the vertices, for the vertices that it's saving, it stores a flag that indicates whether that vertex is at the beginning or the end. So that function features to vertices produce that flag. Make this a little bit smaller. So I've now done the reclassify. So if I zoom to the full extent, you'll see that it has created it's created a raster with zeros most places and just 1 at the ends. But I'm seeing here there's a problem. Who can see the problem? I didn't fill out the extent correctly, so it's left off part of the values. So I'm actually going to have to go and do that again. So
So for any comfort to you, I did this over about 3 times, but I didn't get all the inputs. The inputs go on to a page or 2 here.
So
I screwed this up as well.
coordinate system.
And I just kept on going, and I redid it over a bunch of times and just kept overriding what I did until I finished and got it the right way.
So let's do that. Cell size, same as that. Where did I miss the extent option?
Extend default. They won't system
Oh, there we go.
Yeah.
Default.
goes to
I have to say extent same as onion 3. Okay, so then it'll it's read values from onion 3 and fill those in. So we've got the projection, snap to raster, cell size. Okay.
and everything's good. Yeah, so I got messed up on this too. So when you get to this function, just be sure that you read through all this and just be careful about it, because there's about 5 things you've got to change here, and if you just miss out one of them, you get a mess.
And I even had a red line around it, but
No, well, I mean, I did the same
Yeah.
thing. So it takes a bit to sort of burrow your way in and find just the right place to
Yeah.
make the changes.
so now it's got values of 0 everywhere, and we can zoom in and you can see there's just I guess you have to get really close to see the individual grid cells. So once we've got that, now we're actually at the point where we can do some. We can do the standard sequence of watershed delineation that we did in exercise 4. I thought it would be useful to, as we work through this, be able to visualize what's going on. So I constructed a set of contours for this data set. So I'm going to use the contour function to do that. So surface, I'll just use a contour and spatial analyst. I'm going to create contours of my I didn't actually give guidance for that, but I think just 10 meter contours.
Yeah, so what I did was I added a note in the text here that says, if you want to know how to do this, go back to exercise 3, page 37. So if you look at the text, you'll see that.
Right.
So if you go there, there's a set of instructions about how you constructed contours the last time you did it.
So contour 10 meters, so I think I was going to use 10 meter contours with the contour interval of 10. Interesting that they have a field contour type. What would be a contour that's not a contour? Anyway, let's not go down there. Let's turn off. So now we've got contours. So we're starting to see the topography. And as we develop the drainage network from this, what we're going to probably see, and this might be a good place to keep on our screen, you can see this contour is suggesting that the valley is actually going to go there, but the NHD stream is not following that exactly. So we will probably see that difference. Let me just organize the contours to be the color that's perhaps more common for contours. We can use a light color there and maybe a bit thinner. Let me also turn off some of the other things. So you can see here we've got, this is the NHD stream, and that you can sort of see the shading, and the base map is got the stream in a slightly different place, and we're visualizing the contours, visualizing the topography using contours. So I've got on page 7, I sort of lay out the recipe that hopefully is going to become ingrained. Fill to remove the sinks, flow direction, flow accumulation, create stream raster. Then there's calculation of the flow direction for D infinity, mapping the stream lengths, mapping the watersheds, converting the streams to features, and calculating the vertical distance, which is hand. So let's find the functions to do that. So, okay, that's not a geoprocessing tool. So we're going to be using the fill tool first. That's part of the spatial analyst tools. And if by opening the spatial analyst toolbox, I've got all of the tools handy for getting back to. So let's, and I'm going to save all the results in where am I going to go back a little bit? In this exercise 5 folder, and I was calling everything onion 3 because that was the name of the DEM that we started with. And here I've actually found it useful for myself to sort of invent a language to keep track of which grid is which. And I use FEL to stand for filled elevations. So whenever I see a file that's something FEL, I know it's filled elevations. If it doesn't have any suffix that I recognize, then it's probably just a DEM that I got from somebody else. And you'll see some of these other sort of conventions that I've started using. And it's useful to name things consistently yourself so that you know what the how it's been produced, because the software doesn't. You can name anything you like, but keeping track of it with the software is it's harder then. So this is going through the process of pit removal. I'll let it just continue to do that. And the first thing we need to do afterwards, what's happening here?
I think if you
Just minimize that. So there we got the results. So this is the set of filled elevations. The next function in the sequence is flow direction. And we're going to work with the filled elevations. The output, I'm going to save it as onion 3 FDR, is that what I called it? No, I called it D8. To remind myself that this was the flow directions calculated with D8, because we're going to be using both D8 and D infinity here. The drop raster we don't have to worry about with the D8, we leave it with the D8 flow direction method. So we now should see a result of, wow, this comes back every time I finish a job. We now should see the flow directions calculated here. So this is the encoding scheme we have grown to love and are very familiar with. So the next thing we do is flow accumulation. So we'll use the flow direction raster as input, and where is it going? Onion 3 AD8. So here I was using the contributing area using the D8 method, and good thing I looked at my notes. I'm going to put the W to mean it's a weighted flow accumulation. What I'm actually doing something that deviates a little bit from what we did with the Logan exercise. I'm going to input the weight raster. That's my reclassified start points. So now the flow accumulation is not going to count all of the grid cells that drain into each grid cell. It's only going to count grid cells with that weight value of with that start raster value, and it won't count any other grid cells. I actually was switching to integer here because I know the weight values are integers and the results are going to be integers, and I don't want any rounding to cause cause any errors. I don't think it makes a big difference whether I go integers or floats, except it might make a difference in the time of computation, because this is the one that took the longest time.
Why have you changed this so you're not calculating across the whole landscape?
Because I want the streams to start at the beginning of where there's a mapped NHD plus stream. And that's why I selected that's why I used the feature to vertices to pick out the dangle points of the NHD plus network.
So if you've got a 1 at the top end and then you follow the flow path, then you just get 1, 1, 1, 1, 1, 1, 1, 1, 1 until you get something you want.
Yes,
And
yes,
it becomes 2, 2, 2, 2.
yes.
3, 3, 3. Okay.
And when this finishes, we can show you that, hopefully.
So this is, I hadn't appreciated this, the subtlety here that I missed while I was doing this. After a while, you start gliding, your eyes glaze over a bit, and you just sort of follow
the recipe. So this is a detail to effectively we saw when we were working with the Logan watershed. You can pick a threshold, and if you pick a small threshold, you get a dense network. If you pick a large threshold, you get a coarse network. But what's the right threshold to pick? For this particular network, we actually want to map the height above the streams most consistent with the National Hydrography data set. So we want to start the streams right at them. So here we've got the results, and you can see the values actually scale from 0 up to 42. So that's a much smaller number than you typically are dealing with in flow accumulation. And let's go on to a classified color scheme, and let's go with something that's more bluish to represent streams. And let's actually take the upper value and put it as a value of 0.
I'm sorry, don't even need to.
And then I'm going to make the zeros no color. So let's turn off some of the background layers that we got. So now you'll see what's happened is what we got out of this weighted flow accumulation is this grid that if I look there, look, it doesn't align perfectly with the NHD stream. It started from where the stream was, and if we look at where the start RC is, there's actually this grid cell here. It starts one grid cell down, and that's because of the only count the number of incoming cells model that ArcGIS uses. So you could say we're losing the last pixel, losing the first pixel.
So when I did this, I wondered what start RC, and I started running calculator going, oh, that's that.
Start reclassified.
Start reclassified, yeah, I got it.
So, sorry.
Start off with a thing that says start, and yeah, start RC means start reclassified.
So, but you can, if we look at values as we go along here, we'll see that, okay, if I guess I've got the catchment layer on the top. Let's turn this to have it being selected in the table of contents. So the pop-up will go with this one there. So you'll see that it's got a pixel value of 1. And if I continue to move down, that pixel value will stay 1 until I find where there's a junction somewhere. How far am I going to have to go before I find a junction? So here we've got a value of 1, pixel value of 1. Right below the junction, we've got a value of 11, and we should see that above the junction, we've got a value of 12. Which means that the junction wasn't below and above in the sense. I learned from that when I looked at this, I thought, oh, the water comes down here and heads to the right. It actually comes down here and heads to the left, and you can learn that by just looking at those values. And if I looked at the whole network, I could have maybe seen that. so we've got here, we're going to be basically mapping the streams as this set of blue rasters, because that's where there are the real, that's consistent with the valleys in our digital elevation modeler. And when we're calculating height above a point that we say is a stream, we want to go to the bottom of the valley. Here's a good place to look at it. If we're going to where I've got the little hand pointer here, down to that stream, it's this generalized line that comes from the National Hydrography dataset is not in the same place as the valley from the DEM. That came about because this was mapped from blue lines on a 1 in 100,000 scale topographic map, and this is mapped from a 10-meter digital elevation model that's being constructed much later in the sort of historic process with better data. So the next thing is to then map the streams. So create the stream raster. So here I introduced a new function. Last time we used a threshold. We said if the contributing area is greater than 1 with raster calculator, I decided, well, I was reading in the documentation about watershed delineation in ArcGIS, and they wrote about the condition function, which goes with the name con. So I thought I would just use that to illustrate it to you. So it basically does conditioning of a raster. So I'm going to choose the weights to be that, and now I'm going to add a conditioning clause, and I'm going to say the value has to be greater than or equal to 1. And I'm going to make that as a conditioning clause. And the output raster, I guess I have to say, if this conditioning clause is true, and that's actually the wrong value to put, so let me remove that. I think it has to be, that's, well, I'm getting all lost. Value, I was thinking it had to be greater than equal to, it had to be greater than 0, but greater than 0 is the same as greater than equal to 1. So for this, here I'm going to say, if it's true, I'm going to give it a value of 1. If it's false, I'm going to give it a value of 0. And I'm going to output the results at the location that I'm just going to call it onion-free stream raster.tif. Was there a question there? No, okay. So if we run that, so now we'll see we've got a result that's just got values of 1, the pink colors where there's the streams, 0 everywhere else. That's actually the stream raster that we can use to calculate height above nearest drainage. So I think what I've got next is now the processing to actually do that. We're choosing mostly for maybe personal reasons to use the D-infinity method, but also because I think it's a bit smoother than if we use D8. If you've seen contributing area calculated with D8 and D-infinity, you'll see that there's a difference. And I showed you some of the slides earlier on. So that means we're actually going to have to go back and calculate some of the D-infinity flow directions. So I'm going to calculate that again with the filled elevations. I'm going to output my flow direction raster as onion3 dinf. And I'm going to set my method to be D-infinity. And now I'm actually going to evaluate the drop raster, because later on, you might remember from the lecture last time, we actually need the slope of each grid cell to calculate the wetted bed area. And the way we're going to use the slope is this sort of D-infinity slope that's the drop raster expressed as a percentage. So I'm going to give this a name, and I'm going to call it onion 3 slope percentage. I think I called it percentage slope in the exercise. Is that what?
PSLP.
Percentage slope is what I had in my mind for that. And we're going to run that. This takes a little bit longer, it seems, but
So let me just make some comments while you're doing that. And you may say, well, why should we worry here? Let me say that we recently had a reclassification of NOAA Atlas 14 for Texas, and that's what defines extreme precipitation. And the 100-year 24-hour rainfall increased from 12 inches to 15 inches. That change invalidated all of our flood act. It's been 15 years developing that. It's all broken because now the risk level has gone up. And so now we've got to spend who knows how many years doing that all over again. And even after it was done before, only half the state had been covered. We had half of our state that had no assessment of flood risk at all. And so what we're attempting to do here is to start building some automated systems that can operate at scale, large scale, so that you don't have to do everything by hand all over again when you can change the risk level, or you can change the level of the precipitation.
you are going to do it by hand.
That's true. That's true.
So what we've got here is this is the percentage slope layer, and the values are from almost 0 to 294%. So very flat down up to 300% slope as you go across 1 and up 3. So there's a few sort of steep grid cells in this area somewhere. And we also got the d-infinity flow directions, and those are these here, and they're between 0 and 359. So these are degrees represented as sort of counterclockwise going from east. So now I can calculate the hand value, and so we're going to use flow distance. The stream raster is the target that it's being calculated to, and that's this. The surface raster is the layer that's being used to calculate our distances, our elevations. In that case, I'm going to use the filled elevations. You could debate whether you should actually use the real elevations. I like to use the filled elevations because I like to think of them as actually being our best approximation of what the real surface is, because the sinks are artifacts. And if you don't use them, you sometimes get negative values, which would mean that you're lower than your nearest stream, which doesn't make a lot of physical sense. The result I'm going to save as onion 3 onion 3 hand. And the flow direction raster needs to be put because it's working along the flow direction. So I'm using the d-infinity one. The distance I want to calculate is vertical. There's a choice between vertical and horizontal. And I'm going to use the d-infinity method. So this is flow distance in a vertical sense. And off we go. And now let's have a drum roll while it finishes, because this is the
moment of excitement.
This is the moment of excitement at some level. Yes.
For this exercise, why are you saving all the rasters, not
I just chose to use the GeoTIFF format, and when you save something, if you put the .tiff as an extension, it saves the GeoTIFF format, and that would be a format that you could read in, say, QGIS or even Python or something like that. Whereas if you've got it in an ArcGIS geodatabase, you can really only practically read it with ArcGIS. There are some specialized programs that have sort of cracked, or hacking programs that have cracked the ArcGIS format. But if you save it in an open format, so I guess I'm kind of in favor of wherever possible having data in an open format that's sort of publicly readable by any software or any. So I'm working with that, and also just to show the fact that it can be done, expose you to the idea that there's different formats available.
Let me just add a comment here. So when I was doing the exercise, I found it a little bit disconcerting because sometimes you're saving features which got to go inside of your database, and sometimes you're saving TIFFs which don't. And so you've got to be a little bit careful when you're exercising a series of TIFFs. Each time it brings up a default location, it's looking at what it did last time. And so when you got one TIFF after another, it's okay because it's just putting it where it's last one went. But then when you switch to, now I've got a feature class which is going to come up shortly, then you've got to remember, no, I'm not there anymore. I'm not outside the geodatabase. I'm inside the geodatabase. So you've got to switch back. And that's one of the prices that you're paying for open format.
Right. So, well, I'm also paying the price for the fact that I'm not consistent. Because I could have chosen to put everything in shapefiles.
Yeah.
And then that's also an open format. And then I could have done it all in one folder.
Yeah.
And then the folder would have been a mess because a shapefile is not a single file, it's 7 or 8 files. It used to only be 3 and then they went 4 and they've kept adding bits and pieces to it. So now I'm actually going to, so we see our hand values range from 0, the points right on the stream, up to 122. So there's points in this watershed that are 122 meters above the stream. If you look at our original DEM, you'll see it ranged from 113 meters to 513 meters. So the elevation range over Onion Creek is about 400 meters, but nowhere are you ever more than 113 meters or 122 meters above the stream. So you can see it's just measured the elevation difference to the stream. I'm going to go and re-symbolize this to be able to focus in on the areas next to the stream. So I'm going to switch to a classified symbology. I'm going to go to some sort of a blue color scheme again. And how do I get, I want the dark colors on the left. I'm just reclassifying this. So I'm going to say that there's the first band, I'm going to say less than, the upper value is 2, so I'm going to color that all 2. The next band, I'm going to color that with 5. The next band, I'm going to go up to 10. And then I'm not going to care about the others, so I'm just going to make it no color and make that no color. Make that one no color. So now, it's not exactly the same as I had it in the exercise, but it's probably good enough.
Yeah, so what I did at this point to make it like what's in the exercises, I just manually changed.
So I could go and make this a dark blue and this one a lighter blue, and let's leave the yellow there. So let me turn off some of these other layers that are in the background so that we can see what's going on. So
when we have DEM values, the height values,
right.
then what is the datum that we consider?
It's typically sea level, a geoid. It's either the geoid or what's you know.
Yeah. So we are using here National Elevation Data Set, and the default datum for the National Elevation Data Set is the NAVD 88 datum. So these data have all been set in NAVD 88. It's the more modern of the 2 version datums. So there's 2 datums, two things involved. One is the horizontal coordinate system, which is using universal transversification projection. I assume you're using NAT 83 for that, but NAT 83.
Yes.
Yeah, so NAT 83 horizontal and NAVD 88 vertical. That's what you're working with.
So more or less it is at the sea level.
It's basically,
Yes.
yeah.
So what that means is, you imagine a surface of constant geopotential. That means the attractive force of gravity. And where that exists at the sea, it's approximately the same thing as mean sea level. It's not exactly the same because the sea level actually has topography. It has highs and it has lows because it's got heat and salinity and so on changing its properties from place to place. But so this theoretical surface, which of course goes beneath us here just as it does under the sea, is a surface of constant gravitational potential. That's what it's called. So if you imagine Newton's law of gravitation, you say F equals big G m1 m2 over r squared, then the constant potential is V, which is big G times cap M, which is the mass of the Earth, divided by r, which is the radius of the Earth. That quantity is held constant. That's what the data is.
Yeah, so while he was telling you that, I changed the symbology a little bit so that you can actually see the NHD stream on top of the hand values. So we're seeing that this sort of middle blue is all of the locations that are less than 2 meters above the stream as back from the DEM. The real light blue is less than 5 meters, and the yellow is less than 10 meters. But the stream is not necessarily the NHD stream, because the NHD stream here deviates out from the valleys. The stream we've actually mapped it to is this onion 3 stream raster, which are these purple grid cells. So you can see that's the target of our hand calculation, and that's actually the valley according to the digital elevation model topography. And it's important that you have to map height above nearest drainage consistently with the DEM that you're working with. So there's I guess one of the points coming out in this exercise is that the streams that you map from the digital elevation model don't correspond exactly to what the National Hydrography dataset does. And we've effectively come up with a drainage network that's similar to the National Hydrography dataset by starting at the vertex, the dangling vertices of it, but then following the DEM down using the DEM-based delineation. So I think I've got you to, I've asked you to make a layout that sort of illustrates hand, make a map of the hand raster that illustrates it nicely. So include the NHD flow line, include the contours, legend, tidal scale bar, all the stuff that makes it nice. I asked you to zoom in on some place of interest to illustrate these effects here, as well as to zoom out to the full extent where you can see the big picture, although on this screen it's a bit hard to see the big picture. And when you look at the big picture, perhaps you might want to turn the contours off and maybe even turn the catchments off, or depict hand something like that in the sort of big picture view. So just to round out the analysis, I illustrated, zooming in at one of these locations, I illustrated the difference between the purple lines that are the stream raster and the NHD flow lines. It's handy to have that raster representation as a vector representation of the stream network. So there's still a few steps that we have to do in the processing that we learned from the previous exercise. So I'm going to go back to the geoprocessing hydrology toolset and do the stream link function, and the stream raster. I'm going to use the stream raster that I developed. The flow direction raster, I'm going to use the D8 flow directions, and the output stream raster is going to be called, what did I call it here? Onion 3 link And that's because these are the stream links. This is going to give me a separate number for each stream reach, and then I can use that as a target for the watershed function to delineate the catchments. So let's let that finish. So now you saw that there's numbered from 1 to 106, so there's about 106 links that were delineated. And I can use the watershed function with that as the target to delineate catchments. This is again repeating or reinforcing what you learned previously in exercise 4, I guess. So the input the raster for the core point data. These are the sort of endpoints. I'm going to use the links, the value field, and I think I called it onion 3 catch. So if I run that, we should at the end of this get a raster that shows effectively the polygons draining the entire area. So if I choose to symbolize that a little bit differently, maybe with unique values and maybe some sort of a less aggressive color scheme, and zoom to the full extent. So there we've actually delineated the catchment. So we saw that for the Logan River watershed in the earlier exercise. We also want to convert the stream links to features and the catchments to features to get the vector representation. So I go back into geoprocessing, and I'm going to use the stream to feature function. The input stream raster is link, and that's because that's the one that's got unique identifiers for each link that we can use. It also wants the flow direction raster. It uses the flow direction raster to make the connections correctly at junctions. I named the output, and that actually goes in it's going to be a feature, so it goes in the geodatabase. And I'm going to call that drainage line. So this is now the drainage line delineated from the DEM that's different from the NHD flow lines, and that's going to be something we have to pay attention to later on. And I'm not going to simplify the polygons because I wanted to go through every single grid cell. So now we have a vector stream network that's got this interesting color. So let me go with sort of a purpley color to distinguish it from the NHD blue flow lines. And if we zoom in on some of these places we've been looking, you'll see, for example, now this is the vector flow network, and if I turn the catchment layer off, wherever it is, we would see that it's now following directly along the valley from the digital elevation model that's depicted by the contours, and that hand has been calculated too. We also might be interested in the individual polygons. So to do that, I'm going to use just the raster to polygon function in geoprocessing. So we did that before as well. Raster to polygon, the onion tree catchments. I named the output here catch poly, and I needed to come up with a name that was separate from the catchments that we got from from the DEM. I mean, separate from the catchments that we got from National Hydrography data set. And I also want to create multi-part features in case there's sort of adjacent grid cells that just touch on a corner. We want them to be part of the same feature rather than separate features, and I don't want to do any simplification. So if I run that tool, now we end up with this set of catchment polygons that I'm going to let me have no color and just have the outline, say, colored red. I know Dr. Maven doesn't like red, but we're kind of running out of colors here, so we have to resort to something being red. So if I zoom all the way out here, so the red lines are let me turn off the contours. The red lines are the catchments we delineated, and they look very similar to what the National Hydrography data set gave us, but there will be subtle differences that are about to become important. So,
just to explain why that's the case. So when the National Hydrography data set was developed and the catchments that are associated with it, a 30-metre net depth elevation model was used. And now a more refined elevation data set is available, which is 10 metres, so there's 9 cells for every one. That originally there was just 1. And so if you don't do what we're just now doing, and we have been doing it in the past, what happens is you've got catchment areas that were derived from one data set being used with flow lines and hand maps that were derived from another one. And sometimes there's a mismatch and bad things happen. So the sort of purpose of this is to re-derive all the products from the same underlying data set, so there are two differences.
So I just activated the catchments from the National Hydrography data set, and let me zoom in on. So now you can see, this is getting a little bit cluttered, but you can see the green lines are the NHD catchments, the red lines are our catchments. Sometimes they just differ along an edge like that, because this area, according to the DEM we're using, drains north into that stream, but when the NHD delineated it would drain south into this stream. Sometimes there's also actually places where there isn't any junction, and they've split the catchment because they, for whatever reason, chose to break this single stream reach into multiple reaches and delineate separate catchments. The automated procedure we used didn't do that, so there will be a different number of NHD catchments than the catchments that we got. So I've asked you to turn in a layout that sort of illustrates this and explains some of these differences. So we calculated hand here, and that's used to first map the potential for inundation. If the depth of water is 3 meters, then somewhere you're in between the sort of dark blue and the light blue in terms of what's going to get flooded. The other thing we also spoke about last time was the calculation of the hydraulic properties, the actual weighted perimeter, cross-sectional area, hydraulic radius, sort of averaging along the prism of a stream channel. So this part 3 of the exercise leads you through that, and we're sort of doing it in a hand calculation for just one catchment to illustrate it. I mean, it would be too tedious to try and do it over the whole watershed. We'd have to get into programming, so that wasn't something that we want to do.
Can I make a comment here, Darren?
Sure.
So last week, as you know, the dam was really high, and in fact it peaked on Saturday and it started dropping. But there was potential, it wasn't going to peak, it was just going to go up. And at the top of its height, we had just this much left. Sure, the water went over to build 10 feet, was all that was there. 38 feet before that. So a colleague of mine, Harry Evans, and I, we were going out and collecting pins. So we were actually marking along Town Lake and Lake Austin, where the water actually was when the water's being released from Lake Travis. 28,300 cubic feet per second is being released. So we stood there and we marked, okay, the water is here. We sent pins into an application called Survey 123. And then we could take the hand information that we have here and say, oh, the water level is really there, and there, and there, and there. And then from that, we were able to draw out the inundation map of what was going on Lakes Travis, Austin and Town Lake through the city. And our intention was for this, you get a catastrophic situation where the water was coming over the top of the dam, or over the spillway, that we could be doing the same thing again and marking out just where the water then was, and therefore how large the problem would be or is in case that happens. So we're now going to depart in this analysis and go to a point where we're inferring from the flow how high the water level will be. But just with information products that you've got now, and the use of emergency response personnel or even citizens to say the water is really here, you can actually draw a map from what you have already, the GIS process. And that's a really useful thing because it starts to say that first responders and crowdsourcing can be used to describe the nature of what's going on. You don't have to have computing models to do everything. But just the data by itself and people's observations can help, can actually create knowledge and information during flood events.
So I chose to focus on a specific catchment that was the one that had been subject to some flooding a few years ago. So wanted to find that, and so I'm going to go with a new. So I'm doing select by attribute from the NHD catchment layer. I'm going to search for. It actually had the feature ID equal to this magic number that you wouldn't have known without being told, 5781733. That's just happens to be the one where there were some problems. So if I run that selection, it turns out that we've got, as you can see, let's turn off some of the clutter here.
Before we pass on, why was there a problem here? Look at where the creek goes. Up around there and then down. And what happened? The water said, I don't want to do that anymore. I just want to go across there. And there's a whole subdivision right there. That's where our department secretary was living. So the water just went straight across the neck.
So we're going to make our study in this exercise on this particular catchment. So and it's in the catchment feature class that came from the National Hydrography dataset. But I pointed out earlier that the polygons that we delineated, which are now in red, differ from the ones in green. You can see that there's a chunk of area here that, according to the DEM, actually flows to this stream here, whereas according to NHD, it flows to this stream. If we start calculating hand values and we're counting this area, we're going to be calculating the height above this stream rather than actually above this stream. So what we want to do is identify the corresponding catchment in our delineation of catchments that matches this. So I'm going to do that by basically doing this select, and I'm going to sort of select within that area, and let's turn this off. You'll see that now I've just got this catchment that we want selected. So and then with that selected, I'm going to export it. I'm going to put it in the geodatabase that we're using, and I think I called it catch select. Is that what I called it? Try and be more or less consistent. Catch poly select. Goodness. Sounds like catch the parrot poly and select it, and So run this to actually execute that selection. So now if we turn off some of these other layers, you see there's just a single, I just isolated on this this single this polygon, and I'm going to use that to do some work on the hand raster by basically using the extract by mask just for this catchment. So let's get extract by mask. So we've done this earlier when we were trying to delineate a whole watershed. Now we're just going to do it for the hand layers. For my selected polygon, the output raster, I'm going to call it catch hand, so the hand catchment, and I need to put that in the folder that I'm doing the work. So if I run that, you get so this is the hand raster just for this catchment. So you can see this catchment has values that range from 0 down right next to the stream up to 52 sort of further away. So now we can do some of the calculations to figure out, okay, what are the hydraulic properties of this? So I'm going to do a raster calculation to identify all of the grid cells where the hand value is less than a value of 1. Then later I'm going to do less than a value of 2, less than a value of 5, less than a value of 10. I think I give some suggested values here so you don't have to do too many. If you're doing it automated, you'll go with small increments, but when you're doing it manually, you can sort of do big increments and join these things together. So let's get the raster calculator open. And I'm going to do, so the calculation I'm going to look for when that is less than a value of 1. Sometimes it needs spaces there for it to work nicely, and I'm going to I'm just going to call this lt1.tiff. So that was the less than 1 was the file name that I chose to use. And if I run that calculation, you'll see that it's mostly 0 over the watershed, but if you zoom right in here next to the stream, there's some values of where it's actually less than 1, and I can actually look at its attribute table, and I can see that there's 658 grid cells that are less than 1. So I can immediately calculate, okay, this is the surface area, 658 grid cells times my cell size of 10 meters squared will give me the surface area when the depth is 1. If I do it later for a depth of 5, I'll get more grid cells. So there's information about looking up the cell sizes and things in the exercise. You then want to say, okay, so what's the volume of water involved if we've got this depth? And there's a second raster calculation we can do for that. So now I'm going to say 1 minus, so 1 is the depth of the water. Catch hand is the height you are above the drainage. So 1 minus that is going to be the depth of inundation. So I'm going to calculate that, but I only want to be evaluating the hand for places inside this this area where the depth of water is less than 1. And a trick to do that is to divide by this less than 1 raster. So and close the parentheses and get rid of some leftovers. So this is a sort of a raster calculator trick. If you divide a number by 1, it doesn't change. If you divide a number by 0, it's undefined, which ArcGIS returns as no data. So that's a useful trick to isolate only to the places where you want the result and let everything else be no data. So I'm using that trick here. So 1 minus that, and I'm going to call this the D1. So that's the depth when the depth at each grid cell when the height value is 1. And why is it complaining about this? Okay, just hadn't taken the edit yet. So if I run that, so now you've got values range from 1 to 0, and I can look at the properties of this raster and look at the raster information, or really I have to look at the band metadata. I want to look at statistics. And there's the mean. So the mean depth is 0.713, yeah.
Why don't we straight away do 1 minus less than 1?
Because the less than 1 was a 0, 1 raster that tells you whether it's less than 1. It wasn't actually the hand value. Make sense? Okay. So so I've got the depth of water is 0.713. I can get from the grid cells, I can get the area. So with average depth and area, I've got the volume. So I'm sort of building up the information I need. I've got the volume, I've got the contributing area. From the channel length, I can get the length. And probably the last calculation that I'll do is the raster calculation to get the bed slope. And then you can get that average bed slope, and then you can put things together in a table to calculate the rating curve.
So, I'll make a comment here. So, one of the questions that was raised earlier was, is there a national water model for water quality? And the answer right now is no, but this is the kind of processing that's necessary to create a national water model for water quality, because that requires understanding the volume of water, because water quality depends on the residence time of water in a reach, and how long the organisms have to decay or the sediment has to settle out and so on. So these kinds of numbers can be useful for extending this result beyond just flooding, which is what we're doing.
So this is a little bit of a complicated calculation. We're doing the square root of 1 plus the slope squared. So we have to do square root of 1 plus the slope divided by 100 to get it out of percentages. Paying attention to parentheses times the same quantity again to square it. And then again also divided by this less than 1 quantity to isolate the calculation to where you are. And if I did all that right, I'm going to call this just slope of the bed with a threshold value of 1, and run that.
Is there a way to assign a value of no value to a grid cell without doing the divide by 0 trick?
There may be. There almost certainly is. There's lots of ways to do things. The divide by 0 trick is just the one that I know that works.
Okay.
Yeah, so you can go and find it out and tell us next class.
All right.
I think this function set null.
I tried doing that this morning. I had to do the same thing, but I couldn't get it to work. But I'll show you.
Yeah. So, I mean, this one I know it works, so if you've got one that works, then you don't have to look for anything else. So, it's something. So, we're probably getting pretty close to where I have to end, but what I did there was we calculated the sort of average bed slope was from 1 to 1.004. You can look at its properties and its statistics, and you get the mean as this 1.00104, whatever those numbers are. So that you can then put in a formula for calculating the wetted surface. So we've got sort of set up in the exercise here a table to help you out where you can fill all these things in. We've filled in all the things for this height value of 1, and then asked you to do this, and even got to the point